Okay, so we're going to pick up with where we left off talking about reactions of enolates, and we're going to focus on one of the most important reactions really in both of these classes that happens to be a reaction of an enolate, and that's the aldol reaction. So I think the Diels-Alder reaction is probably like the most fun reaction to talk about because a lot of things happen, but the aldol reaction is just everywhere in biology, in I mean the all of the biological molecules that we use for the most part involve some aldol reaction along the way to generate the carbon-carbon bonds. Okay, so aldol, this isn't a person actually, as awkward as the name is. That's short for aldehyde alcohol. There was no scientist named aldol, is what I'm getting at. And so what this has to do with is we typically in the aldol reaction make a product that looks like this. If you notice, it's got an aldehyde and an alcohol. Okay, great. Now, what I want you to think of when you think of the aldol product is to think the typical product of an aldol reaction is a beta hydroxy carbonyl. This will be much more helpful than worrying about where an aldehyde alcohol unit is. But in general, what you do when you do an aldol reaction is you form a beta hydroxycarbonyl. Now let's break that down. If we have our carbonyl and we look at the framework that's at the top of our notes here, we can see that the OH is positioned not at the carbonyl carbon and not at the alpha carbon, but rather that hydroxyl group is positioned at the beta carbon. Okay, so how does this reaction work? Okay, what we do is we first generate an enolate. And then in step 2, the enolate adds to a carbonyl carbon of usually an aldehyde. It can be a ketone. Okay, so in this reaction, what we're doing is just another enolate reaction, but the electrophile for the reaction is an aldehyde or a ketone instead of a haloalkane, which is what we looked at last time. Okay, so if we go through the reaction, what we're first going to do is take some sort of carbonyl. Let's go ahead and put a benzene ring on one side. And in step 1, we're going to add our base to generate our enolate. That's LDA. Now in step 2, we're going to add another carbonyl. I'm going to, let's go ahead and add like, we can always highlight, but let's add an isopropyl group onto this aldehyde. It's just so we can see what happens to that part of the molecule. And then in step 3, we're going to have H plus workup. Now the outcome of this aldol reaction is we're going to have the typical core of what was our enolate, and then we're going to have a bond from the alpha to the beta position. And now the beta carbon and everything after that comes from the second carbonyl that was added. And then we put a hydroxy group at the beta position. Okay, so there's the product. Sorry, I'll make that arrow a little bit longer. There's the product of the reaction. So it would be great if we all were good enough at this to just recognize the products right away, but this isn't that type of reaction. We have to go through the mechanism at least a few times. So let's do that. I'm going to take my starting material and react it with LDA. LDA serves as a base to pull off the alpha hydrogen atom. And then we could just set that negative charge on the alpha position. We know there's a better resonance structure out there, but we also know that enolates, which is what we have here, and we only have one spot for the enolate to occur. That's not plural, that's just singular. There's only one spot where the enolate can form, and that's the alpha position, which is on the left carbon in this depiction. That's the only one that has alpha hydrogen atoms. Okay, so what we're going to do is mix that with, in step 2, so here's step 1, by the way. Okay, step 2 is we're going to mix that with the aldehyde. Now, the way to think about the aldehyde is not in this form, but rather a resonance structure. Resonance structure, again, is just a different way of describing a molecule structurally that gives us some insight that we might not otherwise have. Now, the negative is going to be attracted to the positive, where the negative comes from our enolate and the positive comes from our carbonyl carbon. Now, drawing these products, just because bond line structures require us to not draw all of the atoms, we have a bunch of carbons together, means that we could run the risk of forgetting some things. So what I do is I draw my enolate structure completely, then I'm going to kind of draw a thicker, here I have the opportunity to color, so I'm going to use a blue line. I'm going to draw a thicker line to the new bond. And this new bond is going to extend from the alpha position, which was on the carbon, the carbonyl originally. This was on our enolate originally, this alpha position. That's going to extend to a new carbon part of it that's part of the carbonyl, and that's the beta position. So here is our beta position. Now the beta position is going to have, in this case, an O minus, because we haven't gotten to step 3, which is our workup step. So that's where the O minus comes from. Let me just get a little highlighting in there. The O minus just comes from that oxygen after the enolate attaches to the carbonyl. And then we have the isopropyl group that comes along for the ride with the carbonyl. Okay, now at this point, we're just going to add our H plus. The negative on the alkoxide is going to be attracted to the H plus, giving rise to our beta hydroxy carbonyl. This reaction is just so important. It's used all the time in biology, and as a result, if you're looking at taking the MCAT someday, everybody loves to throw the aldol reaction and then its partner in crime, the aldol condensation reaction, on tests. It's not overly difficult if you understand enolates, because if you're like, okay, I understand enolates, I know they're nucleophilic and negative at the alpha position, and we just did a bunch of stuff about carbonyls, where carbonyls reacted with nucleophiles by addition to the carbonyl carbon. So you put those, we're basically just merging those two ideas together here. But so this would be a product of the aldol reaction when we form a beta hydroxy carbonyl. Okay, now this is a special example of an aldol reaction called a crossed aldol reaction. But before we talk about those sorts of details in a second, let's talk about the self-aldol reaction. So and maybe I'll just list both of them. There are two types of aldol reactions. One is the crossed aldol reaction, where here the enolate and carbonyl electrophile or let's put it this way. I always have trouble articulating this every year. The enolate comes from a different carbonyl than the electrophile. The enolate comes from a different carbonyl than the electrophile. Okay, that's what we just did up above. We had this isopropyl aldehyde plus this enolate that had a benzene ring on it. So basically the electrophile and the nucleophile were ultimately from different starting points. A self-aldol reaction is different. In a self-aldol reaction, the enolate comes from the carbonyl that is the electrophile. Okay, so let's look at an example of that. Let's say we've got this simple molecule here. What we can do with this simple molecule is treat it with base and a little H plus workup. And the outcome is that we're going to have this product by way of an aldol reaction. We have to be kind of careful under these conditions. This is a harder reaction to pull off, but this is the reaction. We take one starting point and we get to one product. So there's no second carbonyl. What happens here is this forms the enolate and is the electrophile. Now, more specifically, we can look at this in some more detail here. What I'm going to do is I'm going to highlight what we get is if these three atoms, the two carbons and the oxygen, are highlighted in green, in the product, we would see them both here, okay? And then our new bond is like, ooh, blue, maybe? So there's our new bond in blue. Okay. I'm going to go back here. Okay, for this. All right. So we have our new atoms here, or our new bond highlighted separately from the three atoms that were originally derived from the same starting material. Okay, so let's look at the mechanism for the above reaction. So what we're doing here is we're taking some of this, and it has 3 alpha hydrogens. We're reacting it with a base that we assume is suitable enough to generate an enolate. Okay, so there's our enolate. Now the enolate's looking around trying to figure out what it's going to react with. Well, here's the deal. We never just have one molecule used in our reaction. We have like fractions or whole moles of molecules, so trillions upon trillions of molecules. So if one of these enolates is formed, it's going to look around and see if there's a partner that it can react with. And it might just pick itself. That is the starting point that actually hadn't reacted with base yet. So this enolate is going to say, well, if there's nothing else around, I'm just going to react with some aldehyde that still has all 3 of its alpha hydrogens. So there's a few ways we could consider this. We could go with the resonance structure. That's probably the habit I want you to get in. But if you want to add directly here, you just have to push the electrons up. Otherwise, you could add directly to the positive charge. You can do the reaction with any resonance structure depiction of a molecule, just some require fewer arrows to give rise to the product. Okay. In either case, this is the outcome of the reaction. The aldehyde hydrogen now doesn't necessarily need to be drawn. Maybe I could do some highlighting to guide our eyes. This hydrogen corresponds to this or this. We have a new bond in blue here. And then we had these atoms correspond to right here. These atoms correspond to right here. Okay, so there's some highlighting to help map our eye a little bit. And then at this point, we can just do our H plus workup. So the H plus workup is going to give us this, which gives us our fundamental beta hydroxy aldehyde, in this case, our aldol product. Okay, so a general overview of the self-aldol reaction is this. If you've got some molecule A, you can treat that with base to make some enolate, which I'm going to call enolate A. And then molecule A plus enolate A give aldol A. Okay, so an enolate is, or excuse me, an aldol reaction is just some enolate reaction with a carbonyl. And maybe I should have, instead of molecule A, it should have been a carbonyl A. Goodness, come on, off my game. Okay, I should have labeled that carbonyl A. That would have been better. Okay, but anyway, this aldol A is a self-aldol product. Now, conversely, if I had two molecules present, like if I had a molecule A reacting with base to give enolate A, and then instead that enolate A reacted with a molecule B that was also a carbonyl, I would get aldol AB. And then I could flip the order on the two and actually get a different molecule. So aldol like BA would be different, but this would be a crossed aldol product. So hopefully that's a little bit helpful, more helpful than my wordy definition. Here, the molecule that forms the enolate in the crossed aldol, the molecule that forms the enolate is different from the molecule that reacts with the enolate. But in a self-aldol, both the electrophilic molecule, the one that reacts with the enolate, and the molecule that formed the enolate are the same molecule. Okay, so how do we do a cross aldol reaction? Good point. Okay. So how do we do a cross aldol reaction? That is where we have two different molecules. One serves as the precursor to the enolate. The other one reacts with that enolate to give a crossed aldol product. Let's just mix everything together. Let's just mix everything together. How about that? That's a good idea. I'm a big fan of that, mixing the chemicals. Okay, so let's say we take this aldehyde and this aldehyde and we treat them both with some base. What is the outcome? Okay, so in this case we have, let's call this carbonyl A and carbonyl B. So scenario 1, A forms an enolate. In scenario 1, where A forms an enolate, we're going to consider the alpha hydrogens at A reacting with a base to form, we could call this enolate A if we wanted to, but this is just the enolate where we have just that methyl group as opposed to the ethyl group. So now that can react with A or B. So enolate A, we'll go ahead and label that. Enolate A could react with A or B. Now you could prove to yourself that after workup, these are the products you get, where you form a new bond and you have a methyl group. You have a new bond to B, which puts a hydroxy group at the beta position, but also puts an ethyl group at the beta position. Okay? So reacting with A or B. Now what we have here are two products. I'm going to say enolate A reacts with carbonyl A. So I'm going to call that AA, and this is going to be AB. Now in scenario 2, B forms an enolate. Okay. So what if B forms an enolate? Well, B has two hydrogen atoms in the alpha position, so it can react with base. We could pick either one of those two hydrogens to pull off with the base to generate an enolate that I'm going to call enolate B. Now, enolate B could react with molecule A or molecule B, just like enolate A did. Let's see if we can draw the products here. So we have our aldehyde. Now we're going to an ethyl group, and I like to point that ethyl group down. You'll see in a second, it actually makes drawing the new bond a little bit easier. So I'm going to have this in both cases. Okay. Now in one case, we're going to go to an OH. Well, in both cases, we're going to go to an OH at the beta position. Now, if it reacts with A, we just have a methyl group hanging off of the beta position. If it reacts with B, we have now an ethyl group hanging off of the beta position. So I'm going to call this molecule BA. You notice how BA down here differs from AB up and to the right. Okay, just kind of, let's take a second to do that. Compare this structure to this structure. The order of the letters matter because we're going to change the position of that extra methyl group, whether it's hanging off at the gamma position or whether it's hanging off in the middle at the alpha position. Okay. Now, same thing goes with, well, BB is just completely different than AA. But now the order matters here. Okay, so which of these is likely to occur? Well, it's going to be some combination. Some combination of scenario A and scenario B will occur. Giving a mixture. What do we have a mixture of? We have some mixture, and it'll be like sort of statistical, but also substituent dependent, depending on how acidic things are. Hard to predict unless you actually go in the lab. You're going to have some mixture of A, B, B, A, and B, B. And so, did we do a cross-Aldol reaction? Well, kind of. BA and AB, these are cross-Aldol products. But AA and BB are self-Aldol products. These are self-Aldol products, okay? So, we didn't really control for the reaction too well, right? I mean, we got some mixture. It's going to be a little bit based on statistics, and I mean, it's going to be based on statistics and a combination of statistics and reactivity. So how do we get over this? How do we select for like a cross-Aldol reaction versus a self-Aldol reaction? Well, first of all, we could ask the question, how do we select for the self-Aldol reaction? That's an easy one. How do we select so that we only get the products of a self-Aldol reaction? Well, let's think through this for a second. The cross-Aldol products and the what I'm saying is how would I get AA by itself? Okay, how would I just get product AA? Well, don't add any B. If you don't have any B added, then all of the other possibilities are ruled out. And same thing for BB. You just don't add any A. So here, it's don't add a second carbonyl. It doesn't matter that this works for both of them, A and B. Just don't add the opposite one. Don't add a second carbonyl. Okay, so we dealt with that. We got that one knocked out. How do we select for a cross-Aldol reaction? Ooh, cross-Aldol reaction is difficult because there's two cross products that we could form, right? There's AB and there's BA. Okay, so that's an issue. The other issue is how do we have to add that second carbonyl. So how do we avoid the self-Aldol products? So we need to avoid the self-Aldol products altogether and get the correct cross-Aldol product. Well, it turns out this isn't too bad. What you need to do is just be careful about your enolate generating conditions. So you need to generate the enolate quickly and under cold reaction conditions. So oftentimes we do this at like dry ice temperatures, which is conveniently minus 78 degrees. So if you're ever like reading the chemistry literature and looking at old syntheses and you're like, huh, they heat stuff up to like 100 degrees. Okay, I guess that makes sense because that's the boiling point of water. But why do they cool things down to minus 78 degrees? And that's because that's conveniently the sublimation point of carbon dioxide or dry ice. So that's why you see that temperature all the time. So we could generate the enolate under really cold reaction conditions, and we could generate it quickly and in a controlled fashion. So what we do is we use LDA at cold temperatures. Now, does it have to be minus 78? No, it could be 0 degrees or something. Okay, so here's what we do. Let's say we want product BA, which was this product. If we want that product BA, what we do is in step 1, we convert all of B to enolate B under cold conditions. Okay, how does this work? Well, okay, let's take B. Molecule B was this. We're going to add LDA, and we're going to be really good about the stoichiometry. Remember I said when I talked about common bases that you can use LDA is a really nice one because you can control the stoichiometry pretty easily. Sodium hydroxide, if it is a strong enough base to do the reaction, it's kind of hard to control the stoichiometry because as soon as you throw it on the bench or on the weigh paper, it's absorbing water and getting heavier. So it's hard to accurately weigh the mass or determine the mass. And if you can't determine the mass accurately, you can't do the mole calculation, you can't do stoichiometry correctly. Okay, so we're going to do a 1-to-1 stoichiometric ratio. There's no reason to abbreviate stoichiometry. Stoichiometric ratio. So LDA is going to mix with this molecule in a 1-to-1 ratio. And we're going to keep this cold. How cold? It depends. You go in the lab, figure it out. Okay, why cold? I keep emphasizing this, but why cold? So cold temperatures slow the aldol reaction. So if you have cold temperatures, you're going to slow down the aldol reaction, and that will prevent unwanted self-aldol. Remember, we didn't want B reacting with itself. Unwanted self-aldol. Okay. So now all of B is the enolate. So that was step 1, convert all of B to the enolate. Once all of B is the enolate, and it's not reacting with any lingering starting material that's waiting around to react with the base, we can move on to step 2. Just to give you some other background here, the reason why we can cool this reaction down and still form enolate is that when we're doing an enolate reaction, we're letting an acid react with a base. That's just the removal of a subatomic particle, like a hydrogen atom. That's no big deal. But when we do an aldol reaction, that's collision of molecules to form covalent bonds. So oftentimes, when we cool this down, we can really slow that process down or at least stall it a little bit until we hit to step 2. And step 2 is we're going to add a small, doesn't have to be crazy, but a small excess. What's a small excess? That means we're going to have more of this next molecule, which happens to be carbonyl A. We're just going to have a little bit more than we need. So excess, I don't mean excess to sound too excessive. Okay, just a little bit more. That's what a small excess means. Add a small excess of carbonyl A and warm the reaction to enable aldol reactions. So we're going to warm the reaction to enable an aldol reaction. Okay, so what's happening here? So number 1, we want to add carbonyl A add carbonyl A to ensure, sorry, I forgot a word, add enough carbonyl A to ensure all of enolate B is consumed. Okay, so we consume enolate B, and this forms the aldol product BA. So we have all of our enolates sitting and waiting. We want to make sure that we add enough carbonyl A to consume all of enolate B, because otherwise enolate B could react and generate a new carbonyl, because after the aldol reaction occurs, we generate a new carbonyl. Okay, and we can look at that here in a second, or I could just draw it. Here's enolate B. Now I know it's got this aldehyde character to it, but that's not a real aldehyde, because I could show another resonance structure where it's double bonded to carbon, oxygen with a negative charge. That's not an aldehyde. But after we react with carbonyl A, so I guess I'm showing it where it adds to the carbonyl carbon and pushes the electrons up. Now we have a full-blown aldehyde on our product. And so this could react. We want to make sure that we have more than enough carbonyl A present, so that given the choice, carbonyl enolate B is more likely to run into carbonyl A than the desired product of this reaction. That'll prevent some polymerization from occurring. Now, additionally, we should note that no LDA remains here, because we added a one-to-one ratio in step 1. So we wanted to control that stoichiometry. So we don't have any LDA remaining, which means that when carbonyl A is added, there's no enolate around to soak up that, there's no base around to react with that aldehyde and generate enolate A, which would be undesired for us in this particular instance. Okay. So then step 3, add H plus and make product. Okay, so what does this look like from a chemical reaction standpoint? What we're going to do is I'm going to write the reaction this way. I'm going to say that in step 1, I'm going to add LDA, but I'm going to add 1 molar equivalent. That is, for every mole of starting material that I add, I make sure to do the calculation, figure out how much LDA I need, and add a single, the same molar amount of LDA. Okay, in step 2, we're going to add our carbonyl A. So carbonyl A is not present at the outset of the reaction. We first form enolate B in this case. And then step 3, we do H plus. And we could make note cold here, and then the temperature can go where it needs to go after that. If we do that, we should be able to control the formation of our product, which is BA formed. Okay, so the mechanism of this, again, this mechanism is just hugely important, is that in step 1, we're going to have a very controlled formation of enolate B, which exists as 2 resonance structures. Okay, then, so this is step 1. In step 2, this enolate is going to be mixed with an excess, not an excessive excess, but rather a small excess of carbonyl A. And those two add with formation of a new carbon-carbon bond between the alpha and the beta position of our carbonyl to form an alkoxide. We've added enough base so that there's no lingering LDA and there's no lingering carbonyl B. Now, are we going to be perfect? Let's not worry about that. This is an ideal world. Okay. And then we're going to hit this with an excess, a small excess, not an excessive excess of carbonyl A, which will then tell carbonyl or enolate B that that's its only option. If you want to react, you're reacting with me. You're not finding product of the reaction to react with, which is important, especially when the product has functional groups that typically were involved in the reaction itself. Okay. Then in step 3, we are going to work up the reaction to give our desired product. Okay. So here's the thing. There are some other approaches to this if we're curious. So other approaches to controlling for self-Aldol reactions. Okay. This one is just the go-to one was up above, but there are some other approaches if you have the opportunity. So this is these sometimes work. And really they work if the opportunity permits it. If one of the carbonyls does not have alpha hydrogens, if it doesn't have alpha hydrogens, add it in excess. Now we did this in our synthesis of dibenzaloacetone, one of the aldol condensation lab. We'll get to the condensation reaction in a little bit, but what we recognize here is that we use benzaldehyde. Benzaldehyde is a classic example of this. It doesn't have any alpha hydrogens. So what we can do is we can take benzaldehyde, shown here, no alpha H atoms. Okay, it has an aldehyde hydrogen, but that's not going to react with base. And what we're going to do is we're going to use this in excess. Okay, so let's say we want to take this carbonyl and react it with benzaldehyde. In an aldol reaction, we have a lot more flexibility on our base because of this approach. But because we don't have any alpha hydrogens, we can actually just use this in excess, and that will enable the formation of the crossed aldol product where we have that new bond between the alpha and the beta position at from the alpha position of the only carbon with alpha hydrogens to the benzaldehyde product. Now, why does this work? Okay, let's break this down. Okay, let's do step 1. Enolate formation. Hey, there's a ton of benzaldehyde. Isn't that going to interfere with the enolate formation? If we look at benzaldehyde, it doesn't have any acidic hydrogen atoms, so it's not going to react with the base at all, okay? So what we do is we only have one option for our base to start. We just have the alpha hydrogens on this particular aldehyde. So we're going to tug those hydrogens off to give this species, which can react with benzaldehyde. I'm going to draw this down here. I'm just going to move this down here. So I'm just erase benzaldehyde and move it down here. Okay. So we have our enolate. Now, just like before, this enolate has 2 opportunities. It can react with itself and let's go ahead and just let it get protonated. It can react with itself to make a beta hydroxycarbonyl through a self-Aldol reaction. or it can react with benzaldehyde. I'm going to put that carbonyl on the opposite side so you can see it a little better. Okay, so the negative charge adds to the carbonyl, pushes the electrons up. Then H plus to neutralize the O minus gives us our crossed aldol product, where now there's my typical framework of an aldol product. The methyl group at the alpha position, the gamma position has the phenyl group of the electrophile. Okay, so this is now our crossed aldol product. Okay, so here's the thing. First of all, let's recall this. What is the reaction rate? The reaction rate is a rate constant, K, times the concentration of the reactants involved in the rate determining step. For an aldol reaction, the rate determining step is that carbon-carbon bond forming, that big deal reaction. Forming the enolates pretty fast if you want it to be, and then forming the, doing the final deprotonation at the end is really fast. So it's that step in the middle where we do all the action, we form the carbon-carbon bond. That's the rate determining step. So let's focus on both of these processes. What's involved? So the rate of the self-aldol is equal to, I'm going to draw my rate constant K like this, put a little hat on it to tell me that it's like lowercase or something. It's my style, whatever. So we're going to take that, that's just some number, times the concentration of the reactant. So here we have this reactant times itself, because we have two of these in the rate determining step. One is, I suppose, the enolate. Okay, sure. But because the rate of enolate formation is fast, we can just assume that that's equal to the concentration of, anyway, it's the concentration of these two reacting partners. I suppose, is it the base? Well, if the base is involved, I don't think so. Yeah, because it's not the rate determining step. Okay, so it's the rate of these starting materials squared, or concentration of those starting materials squared. Now the rate of the cross aldol is similar, rate constant times the concentration, which is aldehyde 1, which gets converted into an enolate, plus aldehyde 2. So how do you make the cross aldol reaction faster? If this rate is faster, or if that number is bigger, the cross aldol reaction is faster, and this product is preferentially formed. Okay, so then that's preferentially formed if that number is bigger. So how do we make that rate of the crossed aldol bigger? Well, the self-aldol and the cross aldol are similar in that they both include the concentration of that starting carbonyl that gets converted into the enolate. Okay, so what we can do is not really much there. Anything we do to that concentration to try to, if we increase that concentration to increase the rate of the cross aldol, we're also going to increase the rate of the self-aldol, but we have the square of that concentration to consider. So the effect is going to be greater, right? But the thing that's different is the concentration of benzaldehyde is included in the cross aldol. So what we do is we increase this number, the concentration of the benzaldehyde, to make the cross aldol reaction faster. So we just increase the concentration, which, because both of these are just a reaction, we could say the amount used of benzaldehyde. Okay, we just swamped the reaction with this. We can't form a second enolate on it, so it's not going to react with the base. It's not going to hurt us at all. So we just use a whole bunch of it, speed up the rate of that cross reaction, over the rate of the self-Aldol reaction. That's going to give rise to the cross-Aldol product. So the rate of the cross-Aldol to be larger. Okay. So that's how you do it. That's the aldol reaction. Again, one of the most important reactions in chemistry. There's a lot of tips and tricks there. I wish I could say I covered it all, but I mostly scratched the surface. All right, in the next lecture, we'll get into the aldol condensation reaction, which is something that happens to, it's a reaction that happens to the products of an aldol reaction. So I'll see you then.